We spent some time in the last few lectures on the motion of atoms or ions in a crystal, and it turned out that the Hamiltonian can be reduced to a harmonic potential or harmonic-like potential, which gives rise to vibratory motion of atoms in a crystal. And so lattice vibration is a concept which we introduced in these lectures. Uh, but we found out that these oscillations or vibrations are not independent for each atom, rather they are found in the form of so-called normal modes, and normal modes are collective oscillations of a chain of atoms, or you can extend that idea to a three-dimensional crystal. Today, or in this lecture, we're gonna introduce the concept of phonons uh, in the context of normal modes of lattice vibrations. So just to summarize, the treatment for lattice waves or lattice vibrations in a crystal we have done until now. So we started with a continuum approximation in which we treated solid as a continuum of a medium, a continuum medium, ignoring atomic details. And what we considered was, we took an element within the solid, such that we looked at elastic displacements within of a particular element, length element in a one-dimensional case. So this can be either compression or refraction of this element. And we looked at, okay, if you have elastic wave, it would mean that you have elastic displacement which is position dependent. So displacement, there might be displacement here, but there might not be displacement in the neighboring element. So this is kind of a elastic displacement element we took, and we solved for the elastic waves. We solved for it using Newton's law, F equals to ma, for applied on such a elastic element by considering the strain on either side, and the strain on the stress on either side gives you the net force on this element. uh, and we solved for the elastic displacement, and to solve for this we have had such a wave-like equation for these elastic displacements. The solution was a traveling wave solution, which means that this displacement would move um, along the solid, or if you look at a particular position, it would also change with time. So a typical traveling wave solution. We had a solution of this form. This represents an oscillatory function. So what normally we do in real life is we take the real of this solution, and that real of that solution represent the actual situation. It can also be the imaginary part depending on the initial conditions. So this function would give you either a cosine or sine depending on a um, uh, initial conditions. Nevertheless, you do have an oscillatory solution for such elastic displacement in solids. Uh, we extracted the dispersion relation for such waves, and it turned out that the dispersion relation is a simple linear dispersion if you take this continuum approximation, uh, where the omega and k are linked by a constant, and that constant is the velocity of sound in this solid. Uh, so it's linear dispersion. So a dispersion is a relation which connect the spatial frequency with the temporal frequency of any wave phenomenon, and it is a nice linear curve over here. So a linear dispersion would mean that if you make a wave packet of these many different frequencies of such waves, it would have the same velocity as a single wave. So that's one of the consequences of linear dispersion. Um, so this was the continuum treatment of solid. The next thing we did was we took the discussion a bit further, and we treated a one-dimensional solid not as a continuum medium, but rather consisting of atoms. And we assumed the case of monoatomic lattice, in which case all the atoms were of similar mass and the same kind of atoms connected by a spring uh, of a certain spring constant. And this um, description came from the harmonic approximation, because the harmonic approximation tells us that the neighboring atoms interact via a harmonic or a quadratic-like function with respect to each other. So um, what we the wave we made out of was, in this case, was of atomic displacement. So we looked at what are the displacements of any atomic site from its equilibrium position, and then we look for whether these displacements they travel along um, um, the chain or monatomic chain. So there's the potential we looked at. So that's the potential we formed with respect to these displacements. And that's a harmonic potential written in these displacements coordinates. So we applied again F equals to ma for this situation for a specific atom, nth atom within this one-dimensional crystal. And to do that, we looked at from this potential, we extracted the force exerted on nth atom by the neighboring atom, and it turned out to be an expression like this in terms of these displacements or atomic displacement. The solution we had for displacement of the nth atom turns out to be like this, where instead of an x, as you can see here, where x was kind of a continuous coordinate, you have it replaced by an, where a is the lattice constant and n is an integer in general. So where a into n represent a lattice point, in this case the lattice position of the nth atom. So the displacement has this extra feature now that you have the position is discrete positions in this solution representing the positions of the lattice points from which the displacement has occurred. So what were the consequences of assuming such a wave solution as compared to a wave solution like this, which has a continuum-like nature? So we would just to reiterate this thing that you have the solution of this form, but physical situation represent either the real part of this solution or the imaginary part of this solution, depending on the initial condition for that particular nth atom. Uh, as you can imagine, you can form as many such equation of motion as many atoms do you have. So you can basically uh, would indeed have n equations and n initial conditions, and the corresponding displacement for n number of atoms, where n would be capital N, represented by the total number of atoms in the crystal. So the displacement you have in this case is strikingly different. It's not as you here. Uh, it has an oscillatory behavior, with respect to wave number k. Uh, So you plot this dispersion, and it is a periodic dispersion in K-space with a few peculiar properties. So one thing is, because it's periodic, you can define a certain K region, which is called as the first Brillouin zone, in which the solution or the dispersion is unique. And as you go to the next region, the same solution basically repeats itself. So it's important to define a region in K space which has a unique solution, because then you know that the rest of the regions in K space would be simply a repetition of these unique values of dispersion. So if you look at the first Brillouin zone, some striking differences or some similarities between the continuum is that around k equals to 0, this solution which we get from the atomic lattice resembles closely to the solution which you took as a continuum. But the dispersion start deviating from the continuum approximation near the boundary of the Brillouin zone, where the wave numbers or the where the wavelengths uh, start going becoming closer to the atomic displacement. So when the wave of these lattice vibrations, if their wavelengths becoming equal to the dimension of the interatomic distance a, then it start behaving differently from the continuum approximation. And here in this region where the waves are very, very long in terms of their wavelength, they don't feel the atomic periodicity that much, and they resembles that of the continuum approximation. Another striking difference is that there is practically no limit on the value of omega you can have in this case, but here you do have a maximum frequency which are allowed in this monatomic or atomic lattice. So what do you have is, you have basically a band of energies which are allowed to propagate as lattice waves in a solid, and the frequencies which are above them are not allowed. So this is it resembles the case of electrons in a solid. When we start taking the periodicity of atoms in a crystal into account for electrons in a solid, you start having frequencies which were not allowed in a solid. Um, this has uh, slightly different from the electronic case, but nevertheless you do have band formation in which all the energies which are within this energy band are allowed and the rest are not. So to conclude, for lattice vibration, we either have a displacement, a dispersion like this, or a dispersion like this, and neither of these depends on temperature, for example. This here, for example, if you take the atomic, it depends on the interatomic bonding or the strength of the spring constant between the neighboring atoms, depend on the mass of the atom itself. But consider, if we increase the temperature of a solid, the lattice vibration would increase, which is intuitively what you would think. But neither this description nor that continuum description tells anything about temperature dependence for lattice vibration. So you can imagine that these descriptions, either of them lack something, and that's something is the quantum uh, treatment of the problem, and that's what we're going to address in this lecture. We have seen some quantization of k-space, that is, um, and that we did by considering the length of the solid. So for example, if you consider that your solid has a certain length, L, then the K space or the K values get discretized, uh, and they are spaced apart by 2 pi by L using the periodic boundary condition. So when you do that, apply that condition, your K space indeed become discretized, and that's what partly quantization is. Uh, so, and then when you introduce the periodicity of the lattice into the picture, this K space further uh, becomes divided into regions uh, called the Brillouin zones. So you do have this type of classification of the K space and discretization. And when you plot your dispersion, the dispersion relation, of course, would be only true for these discrete values, which are the allowed values of K space within the solid of a certain length L. So uh, last time we looked at this at these discrete number of modes, or these so-called modes of a solid. Each of these discrete values are called modes, and they represent a certain combined oscillatory motion of the crystal itself. And we calculated the number of these modes in the first Brillouin zone, or in other words, the total number of modes which are possible in a crystal, in a one-dimensional crystal which has a capital N number of atoms in it. And it found out that if you consider only longitudinal displacement of atoms, there are as many number of modes as there are number of atoms in the crystal. Um, so uh, this would mean that if you choose a certain, you can choose a certain mode here, let's say mode K, it would have a corresponding omega to it. And for this particular mode, it would represent a certain wavelength of displacement wave within a solid. And in that, when that displacement wave passes through the solid, you can look at the displacement of only nth atom due to that kth mode, and it would be given by such a solution. So you can put this k value in here, and you can put this omega value in there, and you can put the corresponding n value, and you would get this particular displacement of the nth atom due to just this mode of the solid out of all the n modes which are available to this atom within the solid. And of course, any atom, if you take it, would may also have other modes as well apart from this particular mode. But this solution which we showed earlier, it represent the displacement due to only one particular mode out of all these possible n modes. So if you consider not only the transverse acceleration, the longitudinal displacement, but also the transverse vibration. So a longitudinal vibration would represent the displacement along the direction of propagation, and transverse oscillation would represent displacement perpendicular to the direction of propagation of the wave. So if you consider and you can have three uh, different modes, one a longitudinal mode and two different transverse mode, because you can have oscillation into and out of the page as well. If you consider that, last time we found out the total number of modes possible are 3 times n, where n is the number of atom in a crystal. We can extend this discussion to a three-dimensional solid. And let's look at the case of longitudinal and transverse vibrations in a three-dimensional solid, such that all the atoms are of the same type. If you look at a certain crystal, let's say a 2D representation of a three-dimensional crystal, and you have propagation of wave in this direction, so which is, let's say, x direction. So in x direction, this spring would represent the longitudinal vibration, and this spring, which would in the vertical direction, would represent the transverse oscillation. Um, so what you have is that the spring constant now become tensors, because let's say if you have propagation in this direction, which is x, which is represented by the first index, then the spring constant along x would be the longitudinal component, because it would represent the wave motion along the direction of propagation. Uh, but you can have the other component, which kxy, in which x, if x is the propagation of the wave, then y would represent the direction of the spring itself. So that would be that kind of wave, that kind of component of the wave or mode of the wave would represent transverse vibrational mode. So last time, in the last couple of lectures, we have seen that we can relate these spring constants with the physical properties of crystal, for example, Young modulus. So the spring constant between the neighboring atom uh, multiplied by the lattice constant, which is the interatomic distance, is equal to the Young modulus. And we have seen in one of the previous lectures that the Young modulus is indeed C11 component of the compliance tensor. Which means that if you apply strain along one axis and you measure and you apply stress along one axis and you have strain along the same axis. So either you elongate the solid or you compress the solid. So this is the um, kind of relationship between the Young modulus and the spring constant. Because Young modulus is just one component of this compliance tensor. Uh, and now you have spring constant, which have tensor-like properties. You can define your tensor spring constant in terms of such relationship, but no, not in terms of just the Young modulus, but for any component in the compliance tensor. So this tensor you get from the physical crystal as a part of the physical crystal properties. So you take any crystal and the compliance factor, which tensor for crystal is a macroscopic property, which is usually known or which can be measured experimentally. And once you do this, and if you know the spring the interatomic distance, which you can know from the um, X-ray diffraction or neutron diffraction, then you can find the spring constants tensors. So how would the dispersion changes in the case of such a three-dimensional crystal? So you had a dispersion like this, in which you have just one spring constant, which you took as a scalar along one dimension. You took it scalar because you were just looking at longitudinal component of the vibrational. So you needed only one spring constant, and that was a scalar spring constant. But no, even for one dimension, you have transverse as well, so that would need a tensor representation. And of course, for three dimension, you definitely need a tensor representation of this kappa here. So if you have kappa as a tensor in here, the omega also becomes a tensor. So that's, you have a form like this. So where ij can take values of x and y, for example, in a crystal, if your a1, a2, a3 or the lattice vectors are defined along your xyz Cartesian axes. So you can put any tensor vector. For example, if you put kappa xx over here, you would get the longitudinal mode along the x direction. If you put kappa xy in here, you would get the transverse frequency such that the propagation is along x-axis and the oscillation and the displacement is along y-axis. So that would be one of these transverse oscillatory components. So if you draw the dispersion, a dispersion like this, so each k value, let's say I'm talking about k along x, so this k would be only along x. So along x you can have three different frequencies: omega xx, omega xy, and omega xz. This would represent those omegas, those oscillatory motions for which you have propagation of wave along x and displacement is also along x. So that would be your longitudinal component. uh, Omega xy would represent those frequencies or those modes for which the propagation of wave, lattice vibrational wave, is along x-axis, but the lattice, the atomic lattice itself vibrate along or displaces along the y-axis. So that's a one transverse component. You can have the other transverse component in which the propagation is along x uh, and the displacement is along z. That would be the second transverse component. And you can also calculate the maximum values of these omegas by using these tensor components. So the maximum value of this would be 1, and you would, so omega x would have a maximum value given by 2 square root of kappa xx by m. So, and similarly for the two transverse component, the maximum value of these modes are given by these. So uh, for each x, and now you can talk about x for each k, which is the wave vector, and you can talk about wave vector along any direction now. So if you are talking about ky, for example, then the y vibration, y displacement would become longitudinal and so on. So it depends on which propagation you are considering, whether you are considering propagation along x or you are considering propagation along y. If you're considering propagation of wave along y, then this would become ky. And so you can have, if the spring constants along which is kxy and kxz, let's say if these two transverse springs are exactly the same, then these branches would just merge and you would have degeneracies in your spectrum. So it entirely depends on the properties of the crystal or the physical properties of the crystal. Um, how does the wave propagate within a three-dimensional solid? So we can look at the k-space in 3 dimensions. Now, I would uh, confine myself to represent it in 2 dimensional, but you can imagine it to be extended in 3 dimensions. So you have a k-space in your 3 dimension, in 3 dimensional space, k-space, and if you take the boundaries of a solid, let's say a cube, then you can, by periodic boundary condition, the k values along x, y, and z, all these three wave vectors, they become quantized, uh, and they have only discrete values. So given by these three integers and multiple of 2 pi by L of, or integer multiple of 2 pi by L. So you do have only discrete values of k vectors allowed now, given by these. So this is a quantization in 3 dimension space now for lattice vibration. So lattice vibration can have only wavelengths corresponding to these modes, and of course these would be a large number of such. There would be a large number of such modes because the number of atoms normally in a crystal is very, very large, and the number of modes you have is equal to the number of atoms you have in the crystal. In this case, a 3 dimensional crystal. So, so you can imagine that these number would be very, these points would be like really large in number. Anyway, when you induce atomic periodicity on this K space, then you can define a certain uh, region of spaces uh, where the solution is unique and the rest of the K point would just repeat the oscillatory solution of this within this region. So this was so-called our first Brillouin zone, in this case plotted here. So all the k points in the k values in the Brillouin zone, they have unique dispersion, and all the other k points within this three-dimensional k space would be just a repetition of these points. So this was just to complete the discussion for three-dimensional case crystals. So no, because these k values, they are related with omega, so you can define a certain k values. K, you can define a certain omega. So let's say omega, which would be represented by a certain circle inside, and then you can have increase k slightly by k plus dk, and it would represent another circle of omega, omega plus d omega. So you can really uh, uh, draw regions in the k space which have a constant omega, which would represent a constant magnitude of k in the k space. Of course, this was for one dimension, but imagine doing this in three dimensions. So this is kind of a picture you would get. Now, what you can do is you can this circle would have a constant omega. This circle would have a constant omega, slightly larger than the inner circle, and the width of this element is d omega. And then you can ask the question is, what is the density of the lattice vibrations modes within this narrow region of frequencies? And this we already calculated for lattice vibration um, in the continuum regime, and it turned out to be something like this. So this is the density of state function for the vibration mode. This calculation would be exactly would be valid for this atomic description for small values of k's. So that's why you can basically represent, because for small values of k, this continuum approximation is exactly valid to atomic approximation, or the so this is the density of state function in three dimension, and it would be more or less true for small values of omegas or small values of k, where the dispersion of the um, continuum is more or less similar to the dispersion of the atomic chains. But no, the important question is, okay, you have all these available k states or k modes. What would you fill it with? For example, we had such exactly similar description for electrons in a solid. So if you remember Sommerfeld model, we discretize the k space, and then we start filling up those states. So we start from the lowest energy, which would be represented by k equals to 0, and then we start putting up electrons into the states and fill them up until we filled it up to the Fermi surface. But those were the cases for electron. The question for the case here is, because you do have all these modes available, but these are lattice vibrational modes, what would you fill these modes with? And that's where the quantum description is important. So before I describe the quantization of the lattice vibration, uh, I would like to I would like to start with a quantum harmonic oscillator. So, and a principle which is called as quantum correspondence. So if you have a classical harmonic system, any classical harmonic system, which has a normal oscillation or normal oscillation frequency omega, it can be a one mass system, it can be a two mass system, any system, any classical system, but with normal oscillatory modes of oscillations. So you can the quantum correspondence system says that you can construct a corresponding quantum system which would have eigen energies which are not continuous but rather discrete, and their discreteness is given by this quantum number n. And one of the feature of a quantum harmonic oscillator is that you also have energy of the system for n equals to 0, which is mean the lowest energy is not 0, but rather it is something which is called h bar omega by 2, which is a 0 point energy. Omega here would be the normal mode oscillator frequency. So we consider a mass spring system, a simple mass spring system with m um, mass and kappa as the spring constant. Then you can construct a Hamiltonian for this system given by the potential, the kinetic energy part and the potential energy part, where so these you have two dynamical variables here, the position and the momentum in this case, and both of them do not commute with each other, as you well know. And the commutation relationship is given by this IH bar. So what we do to solve this problem is, one way to do it is to construct a certain type of operators, let's say a dagger, using such an expression where I have used these two dynamical variables x and p, or these two dynamical operators x and p. So constructing and utilizing the properties of the mass spring system. So I can also construct a conjugate operator A in this way. These two operators which I have defined, they do not commute with each other, but they have a nice property, and that nice property is this, that you can rewrite this Hamiltonian using these two operators in a much simpler form, and that form is something like this. So once you have this Hamiltonian, you can apply this Hamiltonian on the eigenfunction of the system, and the eigenfunction of the system can be represented by such a form where n may be some integer, and you have a certain eigenvector corresponding to some integer. If you apply this Hamiltonian on these eigenvectors of the system, then you get the energy of the system um, corresponding to the specific eigenvectors. And these energy values are given by h bar omega and integer n plus 1/2, where this integer n would be the corresponding integer to the corresponding eigenvector itself. So these n can attain then values of 0, 1, 2, and so on. And for n equals to 0, you would have the energy, the ground state energy, which is h bar omega by 2, which is also called as a 0 point energy. So a harmonic oscillator has a minimum point. A quantum harmonic oscillator would have a minimum energy of h bar omega by 2 because of this uncertainty between the position and the momentum. So these are important results, and so what we have done here is converted a classical Hamiltonian using by defining such operators into a quantum system such that the energy of the quantum system is now quantized. You can see these energies over here plotted, these wave functions, the corresponding eigenfunctions plotted for different quantum numbers, starting from the ground state energy and so on and so forth. So, and of course the energies also is keep on increasing. So the energy between any two levels in this ladder of eigenstates is simply given by h bar omega. So where omega is a property of this system. In this case, omega would be simply kappa by m square root, which would be the normal mode of this one mass system. So you can look at the role of these two operators which you defined here by applying these operators on these eigenvectors n. So let's say n is representing a certain eigenvector within this ladder of different eigenstates, and you apply a operator to n, uh, you are basically moving from a higher quantum number to a lower quantum number, or to one lower quantum number. So if you apply A on n equals to 3 eigenstate, what you get is the n equals to 2 eigenstate. So this is something which is called as a lowering operator. And similarly, if you apply a dagger on this nth eigenstate, you get n plus 1 eigenstate. So if you apply a dagger on n equals to 3, you would get uh, to the fourth eigenstate. So one operator, it basically it uh, decreases the excitation in the system by moving the system from a higher excitation system to a lower excitation system. And this other operator, it raises the excitation in the system by raising the from one eigenstate to the another eigenstate with a higher energy. So we would use this kind of a description to describe our lattice modes as well. And of course, you can also construct any eigenstate n by starting from the ground state energy, which is represented by n equals to 0. So if you want to construct n equals to 3 state, you have to apply a dagger 3 times. So you excite it for 1 time, then 2 times, and 3 times to reach this. So that's the kind of a formulation to uh, quantize a classical harmonic oscillator and the corresponding operator mechanism. Now coming to the lattice vibration. So you have a chain of a monoatomic chain of atoms, and these monatomic chain of atoms, they do have normal modes of their own, such that each normal mode K, for example, it has its own omega given by the dispersion. And once you know these two values, for that particular mode, you can find the displacement of the jth atom within the lattice for that particular mode. Now, for such a chain of atoms, you can construct a classical Hamiltonian, which we have already done. So that would be the kinetic energy part of it. This is the potential energy part, which is a harmonic potential given by the displacement differences between neighboring atoms and the squares of these. And kappa would represent the spring constant between the neighboring atoms. So if you remember, So we introduce a concept of normal coordinates in the lecture on normal modes. So a normal coordinate is an effective coordinate which represent a combined displacement of all the atoms or all the masses uh, in a system for a particular normal mode, let's say K. So what would it mean here? That let's say if I take K, for this particular K, this atom would be displaced by some magnitude, and similarly all the atoms might be displaced differently using this mode. What then I can do is I can combine all those displacement to make a normal coordinate, and using normal coordinate I can represent just this total the net displacement of this particular mode K. So let's do that, and the recipe to do that is something like this. So xk would be the normal coordinate or the normal displacement for the K mode, for one particular K mode. So how do you do this? To do that, you take the displacement of the jth atom in the crystal, and this displacement may be that is the total displacement, not only due to the kth mode, but from all the modes which are present in the system. So, but you want only that part of the displacement which corresponds to the kth mode. So you multiply this displacement by this factor which contains k and which contains j, which represent the phase corresponding to that mode at that particular atomic position. You get a certain factor if you multiply by this, and that factor is a unique contribution to displacement by kth mode of the at the jth position. And you can add all such contributions to all the atoms for this particular mode K. And to normalize, you divide it by a factor n, square root here, where n is the total number of atoms in the, because you have added extra stuff over here. Nevertheless, what do you get as a result of this procedure is a net displacement or a net normal coordinate for this kth mode. You can do a reverse process, and that is you can find the total displacement of the jth atom from all the modes. So to do that, you take the normal coordinate of one particular mode, multiply this factor, which is the conjugate of this phase factor for that particular K at the jth atom, and then you add uh, these terms for all the K modes which are present in the system within the first Brillouin zone. And once you do this, you get the total displacement of the jth atom from all the modes within the system. So you have these two kind of coordinates which are the Fourier conjugates of each other. This process is also called as Fourier decomposition of the coordinate. So these are the normal coordinates. Uh, you can also define normal momenta of the or the normal momentum of a particular mode. Okay, and the recipe for that would be you take the momentum of the jth atom, which would be the time derivative of the total momentum of the total coordinate displacement of the jth atom, the first time derivative, multiplied by this factor, which would give you the contribution to that momentum by the kth mode at the position j, and then you sum all this up for all the atoms in the crystal, and once you do this, you get the normal momentum of the K, which is kind of the effective momentum for this mode. And you can also find the total momentum of the jth atom due to all the K modes as well. So you have defined these two normal parameters, a normal coordinate and a normal momentum for the k mode, and these two dynamical variable for the k mode would help us to split this problem in terms of mode, so that you can just simply write this Hamiltonian as a term as a summation of over all the k modes. So to do that, you um, define a certain operator corresponding to this particular k mode or one particular k mode k, such that a k is given by this thing, where m is the mass, omega k would be the dispersion, or omega is a function of k, xk and pk conjugate are these two normal variables, uh, and in this way you have defined an operator. So you can now go to, once you have defined these operators, you can go from a classical problem to a quantum problem. You can also define a conjugate operator, should be given by such a description of the um, properties of the system. So you can reconstruct this Hamiltonian now in this easier form. And the nice thing here is that you have split this Hamiltonian into many different parts, such that you can sum all these parts in terms of k. So you can take a particular k and you can find a sub-Hamiltonian for that mode. Then you can find a sub-Hamiltonian for the other mode, and you add all those Hamiltonians up and you get the total Hamiltonian of the system back. So we have written this Hamiltonian, which was a classical, into we have converted into a quantum Hamiltonian, and secondly we have split it into terms of the into modes rather than a sum over the atoms. And this helps us to um, tackle the problem easily. You can look at this whole procedure of quantization of the Hamiltonian of the lattice vibration in these two references. I would also share these two chapters on LMS. So we have this nicer form of the Hamiltonian now, where we have basically decoupled the solution, the Hamiltonian for each K mode within the first Brillouin zone. So now we can, for a particular mode within the first Brillouin zone, we can take the Hamiltonian of that particular mode, Hk, and we can define an eigen state represented by Nk for that particular K mode. And when you apply that Hamiltonian on this eigenstate of that particular mode, what you get is the energy of that mode multiplied by the eigenvector. And that energy of the k mode is simply given by h bar omega k. So if you take a particular k, you would get a corresponding omega for that, and that would be omega k, which is written here, multiplied by nk, where nk would be the quantum number for that particular mode, and it would have value from 0, 1, 2, and so on, plus 1/2. So you do have uh, uh, a ladder-like energy structure for the kth mode. And you can sum these energies for all the k modes into such a summation, and you would get the total energy for the lattice vibrational in the crystal. So you sum up over all the modes in the system to get the total energies. So what are these NKs? These NKs represent the number of excitations in a K, in the kth mode. So what do we mean by this? So to illustrate this, we take a particular K value, let's say K1. It has its by dispersion, the dispersion would give you its particular frequency, omega 1. And then this ladder for this particular K can be constructed like this, such that you have quantized energies for this particular mode. And these quantized energies are given by this quantum number n, so that n for this particular K matrix can be 0, 1, 2, and 3, and so on, depending on which what the value of nk is. So The higher nk, it means that this particular mode has higher excitation, and if nk is small, it would mean that this particular mode has lower excitation. And you can do a similar procedure for any k value, because you have now split the problem into all the k values. So you can take another k2 with its own omega. It's a larger frequency, so here you would have uh, you can construct these ladder for this such that the inter layer distance would be much larger. So what do we mean by going from a lower n to a higher n, or from a higher n to a lower n? So classically it means that you have, let's say, so let's say you take a certain k1. For that k1 you have omega 1. You put these two values in here and you would get the displacement of the jth atom for that particular mode. And if n is smaller, then you would have a certain wavelength of these displacement wave corresponding to that particular mode, because k1 would represent this lambda. But if, as the quantum number is increased, the amplitude of this displacement increases. And as you increase the quantum number further, the amplitude of this displacement increases further. The wavelength remains the same, which means that the k1 remains the same, just the amplitude increases. So going this nk is a quantized version of a representation of the amplitude of the displacement of a particular atom within a mode. So uh, you can choose a certain k vector mode, and for that mode, you can define your harmonic oscillator, the energy structure, and if you can, if you know which eigenstates you are, that would determine what would be the magnitude of your lattice oscillations in that particular mode. And of course, you can have such a construction for any k vector or any k value within the first Brillouin zone, because all of them have unique dispersion. So the role of those parameters ak would be, which is the lowering operator for the kth mode, would be that if you act on it on a certain eigenvector nk, you would get an eigen vector of lower energy by a difference of 1, n equals to 1. So if you start with n equals to 3 and apply this lowering operator on this eigenstate for this particular k mode, you get n equals to 2. And a raising operator would raise it from, let's say, n equals to 2 to n equals to 3 for that particular mode. So the raising and lowering operators comes with an index, because these corresponds to a particular mode now. So so either you excite the system by one quantum number, or you de-excite it by one quantum number, and one quantum of these energies by which they are excited, they are called as these one quanta are called as phonons. So if n equals to 2 is your eigensystem for this particular k, then it would mean that you do have two phonons in that particular mode. And if n equals to 3 for k1, it would mean that the k1 has three phonons in the system. So uh, K1 is one particular state in which so K1 would represent maybe a state of the system, and that state can occupy different phonons. So a many number of phonons, more than one number of phonons. So if you consider phonons as quasi particles, then you can populate each K mode with many number of phonons, which would mean that phonons are bosonic in nature, unlike electrons, because electron can, for a particular k state, you can only accommodate one electron of a particular spin in that k state. But in this case, you can have a substructure, sub energy structure to that k given by this nk. So each k vector would have, because would have a substructure nk, because you can occupy them with different number of phonons in here. So the primary excitation here, or the quantize, we have quantized the problem, and the latest vibration, which was previously a wave, we have quantized that vibration, and each quantum of that vibration is now called as a phonon. This is exactly similar to the quantization of an electromagnetic field, where you take an electromagnetic field, which is a wave of electric and magnetic field, you quantize it, and once you quantize it, you get photons, which is, you can treat it as a quasi particle with a certain energy and momentum. Exactly the same case here for lattice vibrations. So now the question comes is, let's say you have all these k modes available with their own energies. How would you fill up these k states with these phonons? For example, how would you fill up these low energy k state? How would you fill up these high energy k states? What is the procedure to do that? So we got partially our answer that, okay, if you have a k space like this, in which each of these k in three-dimensional represent a certain k mode, you can occupy each of these k mode with phonons. So we partially got our answer that, okay, we can fill up with phonons, but how many number of phonons? And the answer is given by something which is called as Bose-Einstein distribution, because what you are asking now for how many number of bosons you can accommodate in a certain system, in a certain mode of a particular energy, and that distribution of the number of bosons in a certain energy is given by Bose-Einstein distribution, which is given like this, where NB is the number of bosons in a certain state, which has energy, which has frequency given by h bar omega, and because their distribution also depends on temperature, so you have a factor of beta over here, where beta is the inverse of temperature, kb is the Boltzmann constant, and the Bose-Einstein distribution function is like this. So 1 over exponent of that, this factor minus 1. If you look at here, you don't have any chemical potential, because the chemical potential for phonon is 0, which is a boson, and the reason is because you don't need any energy to create or annihilate a phonon, so they are randomly created and annihilated at any particular time. Here you have omega, where omega would be the energy, and the energy is a function of k, which is the dispersion, and for a one-dimensional lattice, it is given by this expression. So this function would tell you how many phonons would you put in a particular k state. And if you plot this NB as a function of energy or as a function of the um, magnitude of k, it is something like this. So it's a kind of an exponentially decaying function, but the important thing here is that the number of particles of bosons which you can have in a certain state of a particular energy, it can be larger than 1. You can put more than 1 phonons in a system. So this tells you that for small k values which have lower energy, they would have higher number of phonons, and as you go away from k equals to 0, where you have a larger k magnitude or larger omega, the population would be small, or less number of bosons would be, or phonons would be there in these large energy states. So this tells you how to fill up, or how to fill up this uh, map. And of course, this is at a certain temperature, which is a non-zero temperature, let's say. this distribution is plotted here. But this distribution has a temperature dependence. So if you increase the temperature, this distribution changes its shape. So here its distribution is shown for three different temperatures, T1, T2, T3. So as you increase this T1, this is the smallest temperature, then you have larger temperature, this is even larger. As you can see here, as the temperature is raised, the number of bosons or the number of phonons in these high energy states, they increases. So the distribution become more uniform. At lower temperatures, these high energy states are empty and these low energy states are occupied, but at higher energies, these high energy states are also occupied. So the energy become more uniform at higher temperature. The distribution of phonons in the system become more uniform. So that's the temperature dependence, which previously was missing in the problem, has now been tackled by introducing quantization into the picture. You can then ask another question is what would be the total energy of lattice vibration in a one-dimensional solid? For example, if you take a one-dimensional solid, then you can construct an integral to find this. So h bar omega would be the energy of a particular phonons of a particular mode K, and NB would be the population of that particular mode. You multiply it here and it would give you the phonon energy at a particular K mode. And you can integrate it from minus pi by a to plus pi by a in one dimensional case, which is over the first Brillouin zone. So if you integrate over the first Brillouin zone, um, uh, and you multiply by 2 pi by L factor, which is what comes with usually with this decay integral, you would get the total energy of the system. You can write L, which is the length of the sample, one-dimensional sample, is N, A, where N is the total number of atoms and A is the interatomic distance, and this would be the expression for the total energy, phonon energy in the system. You can convert this K integral into an omega integral. Uh, this is a procedure which I've already done before. I would leave it to you that you can do such a conversion if you define your density of state, which is a density function, um, and you can basically show that it turns out to be something like this. We have already calculated this density of state for a one-dimensional lattice vibration and for a three-dimensional lattice vibration case uh, for elastic waves, and this would be true. You can use these also for this case as well, especially for lower temperatures. Where in lower temperatures, these higher uh, K values, which represent the K values close to the Brillouin zone, where this non-linearity comes from. For smaller K values, you still have a linear dispersion, and you can easily use these density of state functions to find the total energy. So this is something for you to work out how to go from here to here. So if you now consider lattice vibration in terms of quantum picture and represent it as consisting of so-called quasi-particles called phonons, then just like photons, which are quantum particles of light, you can think about energy and momentum of each particle. So let's say if omega represent the frequency, angular frequency of a particular K mode, then can one define h bar omega as the energy of a phonon and h bar k is the momentum of the phonon. This h bar omega, it's fine, but h bar k has a problem with it. And the problem is this. Let's say if you consider K here, you take a particular K mode, let's say within the first Brillouin zone, then this K is the same as the K which would be somewhere here. So you subtract a reciprocal g with this particular k, and you would reach another k here, which would represent exactly the same physical system or the physical vibration. So a k is equal to a k plus g or k minus g. So what would be the momentum of the phonons then? Would it be h bar k, or would it be h bar k plus g, or h bar k minus g? So that's the problem with defining momentum uh, in this way, is h bar k. So to solve this problem, there is something which is called as crystal momentum, and it's defined as we define something which is called as crystal momentum instead of a momentum of a phonon. And crystal momentum is something which is defined in this way as a momentum modulo of the reciprocal lattice vector, or in other words, you always define momentum with respect to a k vector which is in the first Brillouin zone. So what do we mean by modulo here? So let's say if I say 15 modulo 7, so then it should be equals to 1, because if you multiply 7 by 2 you get 14, and the remainder is 1. So 15 uh, modulo 7 is equal to 1. So similarly, if you have a k prime, let's say k prime is somewhere outside the reciprocal lattice vector, if you take a modulo of that k prime with respect to g, which is the reciprocal lattice vector, then you subtract a g from there. So from k prime you would be coming to a k which would be inside the first Brillouin zone. So that would be the modulo of k prime. So any k prime which is outside the first Brillouin zone can be represented in terms of a wave vector which is inside the first Brillouin zone, and that's what the modulo means. So the phonon, so then you can think about momentum as in terms of crystal momentum and not only momentum for phonon, because this 2 pi by a of the first Brillouin zone, it arises because of the periodicity of the lattice, and that's not a property of a phonon but rather a property of a crystal. So if you define momentum in this way, that you have to take a modulo of any momentum with respect to that of the reciprocal lattice vector, then it is called as crystal momentum rather than momentum of a phonon. So phonon, if you take it as a particle, then just like any other particle, it can scatter off each other. Uh, it can also scatter off from electrons which are present in the system. So you can basically, once you quantize lattice vibration into phonons, you can scatter off these phonons either with respect to each other or from electrons. And the important principle here is whenever this scattering occurs, it has to conserve the crystal momentum and not the momentum of the phonon. So what do we mean by this? Let's look at a scenario where we have three phonons incident um, like this, uh, with a certain k vector given by 2 pi by 3a. Then the momentum of this phonon, let's say the momentum here would be, or the supposed momentum would be 2 pi by 3a into h bar, and the same would be for all the other three. Let's say they get scattered from each other, and they fly off in the opposite direction. So the question is whether such a process is allowed or not. And the answer is it would be allowed only if the change in momentum um, is 0. But the important thing here is the change in the crystal momentum should be 0 and not in the change of the phonons itself. So if you look at uh, this momentum, which was initially in this direction um, or towards this point, you have three momenta which were towards the center, and all three went off in the opposite direction. So you do have a change in h bar k, which are the supposed momenta of the phonon. So that momenta is not conserved in such a event. But the question is whether a crystal momentum is conserved or not. So to find whether that's the case, you have to find the total change in momentum. So the change in momentum of this phonon would be what? It would be twice this incident phonon because it is reflected back. So you have twice the momentum of a phonon, and you multiply it by 3 because you had 3 phonons incident. So this would be the total change in momentum. So whether what would be the total crystal momentum in this case? So you have to take a modulo of this quantity with respect to 2 pi by a h bar, which is the reciprocal lattice vector momentum. So I can, so 3 cancels out. What do I'm left with is 2 times h bar 2 pi by a, and the modulo of this would be with respect to 2 pi by a would be 0 because this is 2 times 2 pi by a, and as we define the modulo here, if it is a multiple of something, the modulo is 0. So this momentum is 0, which means the total change in crystal momentum is 0, and such kind of a scattering is allowed. So basically, you can consider these phonons as particles which can scatter off, and the scattering should only occur if the total crystal momentum is conserved. We have introduced here a process of quantization of lattice vibrations. Um, and this process also sometimes called a second quantization, where you uh, quantize a certain excitation field, in this case the excitation field of lattice vibration. But the question arises, why do we do this quantization process? So one of the reason is that once you quantize it, you have a much accurate description of your phenomenon, because the quantum is the one quantum of excitation would be the uh, minimum possible energy unit of energy which the system either gains or lose. So that is a much more accurate description of your lattice vibration as compared to any classical description can achieve. So that's the one advantage it gives you. The other thing is that all the theoretical or most of the theoretical physical properties which you can theoretically estimate or predict, for example, thermal conductivity or electrical resistivity, they need this phonon description, and they can't be done without phonon description. So we have already treated thermal conductivity and electrical resistivity in this course, but they were kind of a not thorough modeling. They were preliminary modeling exercise just to get you understand what these, how to model the system. But to do proper modeling of thermal conductivity and electrical resistivity, you definitely need a quantized picture, which is the phonons. Then the important thing is that for a theoretician who gonna explain experimental data, because that's what theory are meant for, to explain experiment. So to explain the experiment, you have to let's say they are not uh, easy things to explain. So normally theory is the one which we already introduced in this courses. Some of the theories, they normally fall short of explaining experimental data. So to properly account for experimental data, because practical systems are much more complex, you have to take into account many different physical processes, and you can only do it in a quantized picture. So, so to proper modeling of experimental data, you need a quantum phonon picture. Then many different physical phenomena which you have to explain theoretically, they have to be explained in terms of phonons. You can't explain them in terms of simple classical vibrations of atomic lattices. For example, superconductivity, which depends, whose explanation depends on pairing of two electrons via phonons. So you definitely need a phonon interaction or a phonon description to explain superconductivity. And the And that's the reason, the above are the reason that the language of modern quantum mechanics is the quantized picture. So, or this second quantization picture. And the alphabets of this modern condensed matter physics is are these annihilation and creation operators. So, uh, in modern condensed matter physics courses, which are advanced courses, basically these courses usually start from the second quantization or quantization of phonons. Uh, so to because that's what because these the second quantization or the creation annihilation operator, they form the backbone of modern condensed matter physics. As an example, as I said earlier, that the superconductivity would need phonon picture to describe the processes of a in a superconducting. So the Hamiltonian um, in advanced condensed matter looks something like this, which has these creation and annihilation operators. And you have, for example, you can have events where a phonon at a certain wave vector k is annihilated, and an electron at another k vector k plus k1 is created, and another electron at a wave vector k1 is annihilated. So this would represent one process uh, uh, which is usually used to describe superconductivity, for example. But you take any phenomenon in condensed matter physics and you can construct such Hamiltonians in the language of creation and annihilation operators, which are usually obtained by quantization of electrons and quantization of waves like phonons. You can also have quantization of other excitations in the system, like magnetic excitations, which are called as magnons. So this introduction of these quasi-particle as excitations, they are really form the backbone of advanced condensed matter physics. One great illustration or one great offshoot of this uh, phonon picture is that of the broken symmetry, because what lattice vibration does is it breaks the translation symmetry of the system, and phonons are low energy excitation of such broken symmetry. Just one example of this broken symmetry. So quantized this quantum picture helps you explain also fundamental physics about broken symmetries in the system. So these are enough reasons to that's why a particle picture of lattice vibration is produced is introduced, because this is what's the modern